It is good. You're right. It is important. Okay, here we go. Listen. Here we go. So here's what I want you to do. Let's close those up. If you want to move forward, if you can, get someplace where you can really just focus, be really concerted about just getting this. If you can get it today, you can always re-get it later. You just got to get it today. So you got to really discipline yourself. Well, I'll try to keep this as short as possible. And I think we got a smaller group today. If you're totally with me, I think we can get through this pretty quick. And then you can have a chance to kind of decompress and work on stuff, okay? This is actually still 1.3 stuff. There's almost no problems on this in the assignments, but it's something that's pretty important. And we're going to do this very shortly. We're going to do a lot of stuff with this. So I want to define for you what it means to be an even function or an odd function. And really, in the process of doing this, we're going to do some review of some stuff that's going to help you on all of the assignments, I believe. So, an even function versus an odd function. This is the definition of an even function, but we got to really make sense of what does this say? So this tells us that if I've got some function and I input negative x, if I do algebra on that to simplify it, and I get back the very same thing as f of x, then that makes it an even function, okay? For an odd function, it's a little bit different. For an odd function, if I input negative x into my function, and I get back the opposite of f of x, then that makes it an odd function, okay? Now let's go into a little more detail with that. Let's say we're going to start off with the function f of x equals x squared, okay? Let's make it a little harder, x squared plus 1, okay? Now I want you to think about what it means and really think about this. Don't just, if you can internalize this, it's going to make math so much easier. I'm telling you that in math and in anything that you're learning, any subject, if you can manage to learn stuff on a level that's better than just memorizing details, it stays with you. Memorizing facts, they go away in a hurry, because if you look at real-time imaging of a person's brain, when they're either learning or recalling facts, what happens is a very tiny part of your brain lights up. It's just a very, very small portion of your brain, because the fact is not strongly contained. The fact is it's only got probably one axon and dendrite that's connecting to the neurons locally that contain that fact, and those get recruited for other things eventually, and you lose it. The connection gets weaker and maybe goes away completely. It's not very powerful. But if you can connect something to a concept, when people think of a concept instead of a fact, their brain lights up all over in both hemispheres, because the connections are spread throughout the brain, and so they don't wither. They stay there. Like, for example, I'm a math guy and a physics guy, but I don't remember like formulas. I just don't even bother. If I need to know what the distance formula is, I'm just going to say, okay, it's the Pythagorean theorem, and just kind of think about, okay, so it's got to be this. Every year I have to do it anew for myself, but it takes about 5 seconds, and then I've got it. But I'll never forget that connection, because it's a concept connection. It's not just a fact, right? And you got to kind of do things the same way. You can think of things in terms of processes and concepts. You'll keep them forever, right? So we've talked a lot about f of x, and you guys kind of know how to manipulate f of x, and some of you may be very good and maybe have a really thorough understanding, but I bet you most people don't, sitting in an Algebra 1 class at the start of the year. What does this really mean? This function rule up here, this is telling me, it says f of x, not f times x, equals x squared plus 1. It's just a pattern. It tells me that when I input values of x, I'm going to use this recipe to cook up the y values, right? This is the rule that calculates y, right? So I should be able to put anything in. Anything that it could take the place of that x and would follow this rule. Okay, for example, what if I want to calculate what if I want to calculate f of 3? What am I going to get back? 3 to the second power plus 1, okay? How come? Because I'm going to follow that rule. What does this rule say? What this rule really says is whatever I put in there, let's not even worry about what it is. Whatever I put in there, I'm going to square it and then add 1. right? So that's what I'm going to do with 3. I square it to get 9 and then add 1, and that gives me 10 for my output. Okay, what does that mean? That tells me, that's an ordered pair. It tells me that when I input the x value 3, I get back the y value 10, right? Okay, what if I input I'm going to input an a. What am I going to get back? Seems kind of strange to do, but let's put that away. But it seems like a weird thing to do, but just follow the rule. What's the rule? Yeah, whatever I input, I'm going to square it and then add 1. So I get back the answer a squared plus 1. What's that? Who knows? We don't know what a is, but that's the answer, right? That's what the function kicks out. What if I want to do something even more bizarre? Now this is going to seem really strange, but all you do is follow the rule. What if I want to put in something like, how about like a plus b? What do I get back? Yeah, I get back a plus b, quantity squared, plus 1. Yes?
Question is, if it's multiple like that, don't you have to square both? So you have to do parentheses and basically do just.
You do. In fact, that's a very good question. In fact, you can always do parentheses. I would almost say that it's a good rule, at least until you get really comfortable with this, just always put parentheses around it. Because then, regardless of what you put in there, it's going to work. Whether it's a single thing, or it's a sum of terms, or another function, or whatever it is, if you just use parentheses, it's always going to be the right pattern. Okay, so now let's try our test on this function. Let's go back up and let's try the test for even and odd functions and just see what happens. So what am I going to put in this time in my test? Actually, let's do one more thing first. This will help. There's my pattern, right? What if I put in 2x? What am I going to get back? I'm going to get back the quantity 2x squared plus 1. Okay, but before we go any further, how do we deal with that? Okay, do you remember how to deal with that? Raise your hand if you know for sure. I'm really confident I know how to deal with that. Okay, it doesn't surprise me. I think that's something that you kind of, once again, you probably covered that in Algebra 1, but it wasn't the concept. I mean, so it goes away. But let's think about this as a concept, and then you'll never forget it. So what does it mean to say 2x quantity squared? If I square anything, what am I really just doing? I'm multiplying it by itself. No big deal, right? So this is equal to 2x times 2x, right? Now think about what we do with multiplication. We're good at multiplication. We've done a lot of that. There's some fancy words to describe this, but we don't even really need to know what they are. If we use them, multiplication is commutative and associative, but all that means is that we can move around, we can change the order in which we multiply things, right? Doesn't make any difference. If I'm multiplying 2 times 3 times 4, shouldn't that be the same as 2 times 4 times 3? Right, everybody agree? And I can group them any way I want to, because I have to multiply things in pairs. If I want to find the answer to 2 times 3 times 4, nobody is going to be able to do that in one step, because that's not the way multiplication works. How do you have to do this? Maisie, how would you have to answer that question?
2 times 3 first.
Okay, so we have to say something like maybe 2 times 3 is 6, and then times 4. So maybe we group those first, right? Or what else could we do? We could do maybe 3 times 4. We could group and then get 2 times 12. Either way, we're going to get 24, but we still have to group them in pairs always, right? But we can group any way we want to, and we can move around all the pieces any way we want to. So look what this does for us. Then if we take this 2 times x times 2 times x, well, first of all, let's just write it like this for a second. Those are the 4 things we're multiplying together. How do you think we might want to group those? I mean, how do you think we would reorder them? What? Okay, yeah, okay, let's put the, good. So let's do the 2 times 2 first, and then the x times x at the end. And let's group maybe those 2 together and those 2 together, right? So what is this really? Well, that's just saying 2 squared, which is 4, right? And this is saying x squared, which is just x squared. right? So could we have taken a shortcut then? If I had something like 2x squared, isn't that really the same thing as just squaring the 2 and squaring the x and multiplying them together? So there is a property of exponents that allows us to do that. If I've got a product of a bunch of factors taken to a power, I can just apply the power separately to each of the factors. And that's why, right? We did a pretty limited case with just a squared, but we could have done this with much bigger exponents if we wanted to. It'd still work, right? So what if we wanted to do something like 3x to the 4th? How could I make that, how could I simplify that? Yeah, it's just going to be 3 to the 4th times x to the 4th, which is 81 x to the 4th. How do I get that so fast? It's not hard. 3 squared is 9, and 3 squared squared is 3 to the 4th, so it's 9 squared, right? But don't worry about that. I mean, we could do that in a calculator if you wanted to. We'll get to those properties later, right? You see how that works? So then if we go back up, now let's try our test. Now this will go fast, because now we kind of have an idea how to deal with this stuff. Okay, so what about this? So let's try putting in a negative x. We'll follow our pattern. Notice I haven't even put in I just wrote down the function pattern first, and now I can plug in what I'm going to stuff into f of x, right? A negative x. Okay, so how are we going to simplify that? What number does that negative sign represent?
1.
Negative 1, right? We don't write the 1, we just write the negative because we're lazy, but that's fine. We know it means negative 1. So what is negative 1x squared? Isn't that the same thing as negative 1 squared, right? Which is what? 1 times x squared, which is x squared. We're going to do this a lot. When we plug negative x into a function, a lot of times it's going to be taken to powers. And so we're going to be taking that negative 1 to a power. There's only 2 possible outcomes. If I take negative 1 to any power, what are the two answers I could possibly get? 1 or negative 1. When am I going to get 1? If I take negative 1 to what kind of power will I always get a positive? To second or fourth, any even power, right? If I take any negative number, including 1, to an even exponent, then I'm always going to get a positive outcome, right? So negative 1 to any even exponent, always 1. When would I get a negative answer? If I take negative 1 to an odd power. Yeah.
Does that
right.
happen with any number or just only 1?
It works with any number. Any number. Yeah. So for example, if I take negative 3 cubed, I'm going to get back, what's the sign of my answer going to be? Negative, right? Because I got a negative to an odd, right? And then 3 cubed is just 3 times 3 is 9 times 3 is 27, right? But if I take negative 3 to the 4th, I have a negative number to an even power, so what's the sign? Positive. And then 3 cubed is 27 times 3 more is 81. Okay? See how that works? Okay, so then look what we get. If we go back to our problem here, what was the outcome? So I got, this became x squared plus 1. That looks familiar. That's just the original function, right? So when I plugged in negative x, I got back f of x. It's even. You see that? You see what I mean by that? I got back, when I put a negative x into this function and simplified, I got back the original function. So I passed the test for an even function. Okay? Let's try something that's going to turn out to be odd. See if you can tell me why, too, here in a second. See if you can see, there's a shortcut to this, where we can even just skip all the work and just say, aha, I know that one's even, I know that one's going to be odd. How about this one? Let's say f of x is x cubed minus x. So let's evaluate this at negative x. So first of all, let's, like we always do, let's just write down the function pattern. Right? Doesn't this say that whatever I input, I'm going to cube it and then subtract from that the value, right? Okay. So f of hand is just hand cubed minus hand, right? Well, in this case, hand is gonna be a negative x. Okay, what's that give us? So let's look at this first one. I get negative x quantity cubed. So negative 1 cubed is negative 1, right? Because it's odd, it's going to stay negative, and then x cubed is just x cubed, right? Minus negative x, if I subtract a negative, what do we get? Okay, now I want you to look at this result. Compare this to this. How are they different? Say it again. Okay, they're opposites, aren't they? Because look, this one started off being positive and ended up being negative, the first term. The second term started off being negative and ended up being positive. Yes, ma'am.
How did you get the negative x? Like, why did you? Oh, never mind.
Are you sure? Over here?
Yeah. No,
It makes sense? Are you sure? So we plug in a negative x, right, into this function. So we get negative x squared plus 1, but negative x squared simplifies to just be x squared because it's an even power, so the negative sign goes away. See what I'm saying?
Yeah.
Okay. Over here, look what happened. When we plugged in the negative x, each of these terms became the opposite. Well, let me ask you something. What number would I have to distribute into this original function? If I multiplied f of x by some number, I could change all of the signs of each term. What would that be? What number would I have to distribute through? So what times x cubed would give me negative x cubed, but would also make negative x into a positive x? Negative 1, right? Multiplying by negative 1 just makes everything the opposite, right? And so do you agree that what we have right here is really just the opposite of what we started with? You see that? Okay. So that's an odd function. See what I'm saying? Now, there's a trick to this. The words even and odd are really significant here. Now, let's take the odd function first, for example. What do you notice about all of the exponents up here? What is the exponent of just plain old x? Thank you, sir.
Yeah.
Oh. What's the exponent of just a plain old x? 1, right? We don't write it, but it's there. Okay, what can you tell me about, how would you describe each of those numbers? 3 and 1, those are both odd. What do you know? So whenever we take a string of powers of x that are all odd, it's an odd function, for sure. Okay, there are other kinds of functions that's not so obvious. Like if we deal later on in life, we deal with sine functions and cosine functions and tangents. Well, those, it's harder to tell. We have to apply the test to those to see if they're even or odd. But if we're dealing with polynomials, which is a fancy name that we'll talk more about, but all it really means is we're adding up powers of x, adding or subtracting powers of x in our function. If all of them are odd, then it's an odd function. Now, how is this even then? This is tricky. What power of x do you suppose is actually there, but we don't write? 0. Yeah, because remember, anything to the 0 power, this goes back to algebra 1, anything to the 0 power always equals the same thing, which is what? No, 1 equals 1. Yeah, it's called the 0 power property. And it's true for anything except 0. 0 to the 0 doesn't make sense. But any other number taken to the 0 power is always equal to 1. So we've got an invisible x to the 0 there that we would never write. But the point is, this works then because 0 is an even number, isn't it? Think about the pattern. -4, -2, 0, 2, 4, 6. It fits right into that pattern. 0 is even, right? And so that's an even function. Okay. Now, last thing I want to do, and then I'm going to let you work. Let's look at, there's something really significant about this. Why do we talk about even and odd functions? The main reason we talk about them is so we can essentially cheat and be lazy. So we can take advantage of the fact that there is a symmetry that always goes with each of these types of functions. In my calculus class, we do a lot of stuff with this. We do a lot of complicated work trying to figure out what a curve looks like by using calculus. But if we know that the function is even or odd, we can cut our work in half. And here's how. Let's look at an even function for a second. What does this tell us? It tells us that if we input a negative x, we get back the same y value as if we input a positive x, right? So let's just say hypothetically on the xy plane here, let's just say that that's the value of x. And let's just say when we input that into our function, this is what we get back for the value of the function. So let's just say that this y value is f of x. So the coordinates of that point are we input x and we output f of x. Now I haven't been specific, right? But if that's true, if moving over this far to the right is x, then wouldn't moving over that far to the left have to be negative x?
Yes.
Agreed? Well, if it's an even function, then f of negative x, when I put that into my function, I get back f of x. So the point's going to be there, have the same height. Now, what kind of symmetry do you see here between those two red points? Is there something, could we generate, if I wrote down the first red point, is there a symmetry that would have allowed me to draw the second red point without doing anything?
Yes.
What is it? How could I, what symmetry is there about those 2 points? Maybe that one. Say it again? What is it? There's a line right there. Is there something symmetric about that line compared to those
Yeah.
2 points?
Is it like they have like the same like opposites like the x value?
Okay, it is. It's folding symmetry. Wouldn't you agree that if I fold the plane over, pretend it's a big piece of paper, if I fold the plane over along that crease, those 2 points line up perfectly? So that's reflective symmetry or folding symmetry, or sometimes we say line symmetry. Same thing, right? So where would, for example, if I input this point, it ends up being like right here. Let's say we input this x value and get back that y value. If it's an even function, where is there going to be another point that's symmetric to that one? Instead of going over one and up one, go back one and up one, because they have folding symmetry, right? You get that?
Yes.
If I draw the whole curve, who knows what it looks like? I'll just make one up. It might look like that, where if I fold it over, it perfectly overlaps. It has to perfectly overlap. So do you see the advantage of this? If I know what one half of the curve looks like, I don't even have to mess with the other half. I can just fold it over to get the other half. It's symmetrical, right? Okay, that's even symmetry. Okay? Even symmetry is line symmetry about the line y equal, about the y-axis, sorry, right? So folding line symmetry about the y-axis. Okay, what about the other one? Let's try this guy. What does this say? Same deal. So I'm going to go over some distance x, and let's say that maps us up here to f of x. So my point then has coordinates over x, oh my gosh, it's over x up f of x. What does odd symmetry say? If I go back negative x, it tells me that my y value is going to be the opposite of f of x. So instead of going up that far, I have to go down that far. How many is that? 1, 2, 3, 4. So right down here, right? So right there. There's the point x negative f of x. Now, do you see something about this symmetry? This is a little harder to see, but I'm going to help you out a little bit. Let's draw a line segment connecting those two. What do you notice about that line segment? Where does it go through? It goes through the origin. It goes through the origin. Now look at this point right here. In fact, where is that point relative to the other two?
He's right out middle.
It's in the middle. It's the midpoint, right? Now, we didn't pick any special point. We just picked a random point x. So if I do the same thing again, let's say we pick a point like right, how about right here? Oops, right here. Right? Well, if I want to find the symmetrical point, it's got to be the one that's right down there, right? So the midpoint is the origin is the midpoint. Agreed? Okay, do you see that that's not folding symmetry? Because if I wanted to fold to get this point down to there, I'd probably have to fold the paper like right there, right? That's going to be the wrong fold to get that point from there to there, though. Right? Point symmetry is not folding symmetry. Point symmetry is different. Point symmetry is spinning or rotational symmetry. how could I get, if I put a tack in this big piece of paper up here, let's say I put the tack right at the origin, right there, how could I get from this point down to that point? How far would I have to rotate the whole paper?
180.
180, right?
Yeah.
It's gonna be half a turn. It's just gonna go clear around like that, agree? Wouldn't the same thing happen here? If I rotate 180, isn't this one just gonna go half a circle to get there? Okay, so then odd symmetry is rotational symmetry about the origin. So we're gonna, if I take a function that's odd, I'll give you an example. Like here would be an example of an odd function. That's half of it. The other half would have to look like this, because that's the half that I would create if I just spun this thing half a turn. And that is, for example, that's the graph of f of x equals x cubed, which is an odd function, right? Odd power of x. See that? That's good. By knowing half of it, I can spin it to recreate the other half. I don't have to find it. I can just do half and then draw the rest because I know what the symmetry is. Make sense? Okay, so odd function is point symmetry or rotational symmetry about the origin. All right? We'll come back to that a lot. There's not that much of it in chapter 1, but later on we will. Okay, have at it. You have a little time. Go. Okay.